This series of lectures is about how to take an algorithm and to count its primitive computational steps in the form of theta of f of n for some f of n when it's applied to an input of size n. So for example, for insertion sort, we will show that it takes time theta of n squared. That is to say, f of n equals n squared. Whereas for heap sort, f of n equals n log n. That is to say, heap sort takes time theta of n log n. We'll be analyzing two different kinds of algorithms, recursive ones and iterative ones. In the case of recursive ones, they call themselves, and so when you have a file of size n, it will call itself one or more times with subfiles of size smaller than n. For example, size n over 2. The result will be an analysis T of n that includes the times to run on these smaller size files that are recursively called, these smaller size inputs. And this will yield an equation that is called a recurrence relation. Then we need to solve the recurrence relation, which means to compute from it, or to get a value explicitly in the form of Tn equals theta of f of n, rather than T of n in terms of, let's say, T of n over 2. So for recursive algorithms, we'll be forming and then solving recurrence relations. For iterative algorithms, these algorithms have loops. And so let's say the loop goes from I equals 1 to n. The body of the loop can be analyzed for its time. And so the loop body for the ith time will get a time, and I'll call that t sub I. And the total time will be the sum from I equals 1 to the number of times around the loop, let's say n, of t sub I. That is to say, the computing time will be in the form of a summation. And then we have to turn that summation into the form theta of some f of n. And we'll be seeing how to do that as well. To make this more concrete, our first examples will be 4 sort algorithms, namely insertion sort, quicksort, heap sort, and merge sort. Insertion sort is an iterative algorithm. It works by starting from the second element, understanding that the first element is already a one-element sorted file, and inserts the second element into the one-element subfile above it, so that it ends up with a two-element sorted subfile at the beginning. And then the third element is inserted into the sorted first two, producing a 3-element sorted subfile at the beginning, and so on up till the nth element, which is inserted in the sorted subfile of length n minus 1 of elements 1 through n minus 1. So it's iterated. It is an iterative algorithm which iterates over the successive insertion of elements 2, then 3, then 4, up to n. Quicksort is a recursive algorithm. It's initially applied to sort items 1 through n, and it operates by choosing one of those elements as a partitioning element and comparing each of the other elements to it on the basis of their keys. Those elements that have keys less than the key of the partitioning element are put in one subfile, and those that have keys that are greater than or equal to the key of the partitioning element are put in another subfile. And then quicksort is recursively applied to the two resulting subfiles. This is a recursive algorithm. It calls itself with subfiles of size smaller than n. Heap sort, it is an iterative algorithm. It involves first putting the file into the form of a heap, which makes the maximum element be at the top of the heap and thus be easily accessible. It then puts that maximum element into its final place as the nth element by swapping it with the nth element, and leaving a subfile of size 1 through n minus 1, which is not a heap, but which can be made by reheapifying, at which point the max of that subfile of size n minus 1 is put into place at position n minus 1, and so on, successively putting in the n minus 2th in place, then the n minus 3rd, and finally down to the first. So it's an iteration, if you will, putting in the elements into the file in reverse, in order of the largest at the end down to the least at the beginning. Merge sort is a recursive algorithm, right? You're familiar with it. It divides the file into two parts, each of size n over 2. It then calls merge sort on each, and then takes the two sorted subfiles and merges them. So let's be more specific, starting with insertion sort. As I just said, insertion sort is an iterative algorithm, and at the ith stage, items 1 through I are already ordered by their keys, and we want to insert the I plus 1th element into that list of I sorted elements. More precisely, we need to compare the I plus 1th element to the one with the greatest key of the first I, that is to say the last element, the ith element. And if the comparison set results that the I plus 1th element's key is less than that of the ith, we want to put the I plus 1th down into the, we want to put the ith down into the I plus 1th position and move the element we're presently inserting into the ith position. That is to say, we do a compare, and if, depending on what the comparison gets, we may swap the I plus 1th and the ith. Once we do that, our element to be inserted is in the ith position. Of course, if there was no swap, we can stop, but at worst, we will have to swap. Then the ith element needs to be inserted in the first I minus 1. And so we play exactly the same game. We compare it to the I minus 1th, and if necessary, swap, and continue that until the element to be inserted is greater than or equal to the element being compared, in which case we can stop the process for this iteration. So at worst, when we're inserting the I plus 1th element, it has to end up in the first position. And so we have to do I compares and I swaps, compares to all of the elements above, and keep swapping until it gets put up into the first position. The result, that is that step I of this iteration takes I swaps and I compares. We'll let the swap and compare combination be a computational step. And at worst, it takes I of those. However, on the average, we only need to make I over 2 swaps. That is to say, the element being inserted on the average only has to go halfway up into the sorted file. The result is that at worst, the total number of swap compare steps, at worst, that's the sum over the loop index, 1 to n minus 1, of I, the number of swaps and compares at worst. Well, we have a formula for that summation. It says that that sum is n minus 1 times n over 2. And that's a constant times n squared plus order n. That is to say, it's theta of n squared. In the average case, instead of doing I swap and compare combinations, we only on the average have to do half as many, which means that the sum is half as big as the sum in the at worst. But multiplying by a constant factor of a half doesn't change the order. So insertion sort is a order n squared algorithm, both at worst and on average. Now let's go on to analyze quicksort, at least in its worst case. Later we will be analyzing its average case, but not for a while. Let's remind ourselves what the quicksort algorithm is. The quicksort algorithm is applied to a file with indices that go from 1 to n. That is to say, a file of n elements. But it makes recursive calls for files with different indices. And in general, we will be calling quicksort on a file from the ith through the jth indices, where j is greater than or equal to I. Of course, initially, I equals 1 and j equals n, but in later calls, I and j may be different from 1 and n respectively. Okay, so if I is equal to j, we have a one-element file. It's already sorted. There's nothing to do. We return. But if I is less than j, we have a file of 2 or more elements, and we will pick the one with the last index, the jth, as a partitioning element. And we then need to compare all the other elements, that is to say the ith through the j minus 1th, to it. And if an element being compared is less than the partitioning element in its key, then we will put it in one subfile. And if it's greater than or equal, we'll put it in the other subfile. Thus, we produce 2 subfiles. And we can put the partitioning element between those 2 subfiles It's in the right place now. And we then have to apply quicksort to both of the two subfiles. Now, on the average, quicksort does well. And in particular, it does well when we divide the file roughly equally at each stage, so that the two subfiles, the less than subfile and the greater than subfile, are about the same size. But that's not the worst case. So let's go on and think about what the worst case is. The worst case is when at the kth stage, that is to say when we're partitioning k entries, we find that all the entries are either all less than the partitioning element's key in key value, or all of them are greater than in key value to that of the partitioning element. So it's dividing the file into the partitioning element and a subfile of size k minus 1. Only then do we have a file of only one element smaller than we had, and we have to quicksort it. As a result, the recursion calls quicksort n minus 1 times. One to get from n to n minus 1, one to get from size n minus 1 to n minus 2, one more to reduce the file size to size n minus 3, and so on. Moreover, at the stage where we're dividing something into 1 and n minus 1, we had to do n minus 1 comparisons and placements. And we'll call that comparison and placement cost, the primitive cost. And there are order n of those comparisons and placements. So what we've shown, in worst case, T of n, the time to sort a file size n, is the time to sort a file of size n minus 1, plus this cost of comparisons and placements, which is theta of n cost. This is a recurrence relation. The recurrence relation has to be solved so that we can get T of n equals theta of something. This particular recurrence relation, though, is pretty easy to solve, because we notice that at time n we have theta of n work. That is to say, work that's a constant times n plus negligible terms. Then we have to sort the files out n minus 1, which is going to be the same constant times n minus 1 plus negligible terms. And then we have to sort a file of size n minus 2, which is the same constant times n minus 2 plus negligible terms. That is to say, we have an overall cost of some k equals 2 to n for the files of size k files of size n minus 1 down to size 1 of theta of k work. Now we know that the sum of that k equals 2 to n of theta of k is the same as sum k equals 2 to n of k in regard to k theta value. That is to say, it's theta of n squared. So insertion sort is an order n, quicksort is at worst an order n squared algorithm. Of course, we've seen that insertion sort is also at worst an order n squared algorithm. I want to point out, however, a difference in how we analyzed quicksort from insertion sort. In insertion sort, we had an iterative algorithm. Here we had in quicksort, what is a recursive algorithm, and as a result, it produced a recurrence relation. T of n equals T of n minus 1 plus theta of n at worst. And then we had to solve that recurrence relation. It so happened that solving it generated a sum. That's not always the case for recurrence relations, but it is here. And as a result, we were able to produce the final form of T of n by evaluating a summation formula. Now let's analyze heap sorts, worst case. To do so, we need to remind ourselves what a heap is. A heap is, first of all, a binary tree, stored as a one-dimensional array. The root of the binary tree is stored in the first position in the array. Its two children are stored respectively in the second and third elements of the array, and they're understood to be at the second level of the tree. Their four children are stored in the fifth, sixth, seventh, and eighth. The fourth, fifth, sixth, and seventh elements of the array, and they are understood to be at the third level. And so on, down log sub 2 of n levels. We will assume that the bottom level, the leaves, are all there. That is to say that there are exactly the log 2 of the number, that there are 2 to the number of levels minus 1 elements in the file. If not, the analysis remains the same in terms of the function theta. So now we remind ourselves that heap sort consists of first taking this file, which is initially a binary tree that is not a heap, and making it a heap. We call heapifying that. And once it is a heap, there is a loop that successively puts the largest of the unsorted elements that into position, so that the first time of the heap, the nth element's put into position. Second time around the loop, the n minus 1th element is put into position, and so on. In the process of putting that into position, the element that was in that position is swapped up to the top of the heap. And thus, we need to restore the heap, at least with regard to the unsorted elements so far. So we have heap sort is a heapify followed by a loop of successively putting each next, the largest, and then the next largest, and the next largest, so on, into position, and then reheapifying. Okay, so we're now ready to think about analyzing heap sort's worst case. In order to do so, we have to first analyze heapify, and then we'll have to analyze the loop. We'll begin, however, by analyzing heapify. Okay, in terms of analyzing heap sort's worst case, let's first describe heapify, its first stage, via the basic number of its computational elements. And we'll see that each computational element is a comparison among three elements, a parent and its two children, followed possibly by a swap of a parent with a child. Initially, the binary tree doesn't satisfy any of the heap properties. That is to say, there's no particular relationship between parents and their children. However, if we look at the leaf elements, of which there are n plus 1 over 2, there are, each one of them forms a simple element with no children, and so automatically satisfies the heap property. That is to say, we need do nothing for the n plus 1 over 2 elements at the bottom of the tree. So we move up one level, at which there are n plus 1 over 4 elements. For each one of them, we're going to do this basic computational step. We compare the parent with its two children, and we want to get the heap property. We find the larger of the three, and we swap it with that child. Of course, if there was no swap necessary, then we already have the heap property. We have to carry this basic computational step of three comparisons and a swap at worst for each of the n over 4 elements, or n plus 1 over 4 elements at that stage, at that level. So we have n over 4 total of these computational elements to do. We can then move up to the next stage. There are n plus 1 over 8 of those. That plus 1 in each case is negligible and won't affect, so I'm just going to say n over 8 from now on. For each of those n over 8, we have to do the basic computational step with regard to its children, thereby getting the maximum of the three in place and swapping with one of its children at worst. And then that child now has the former parent in its place, and it may not satisfy the heap relation with regard to its children. And so we have to redo the computational step with regard to that little subtree, requiring 2 of the computational steps for each of the n over 8 parents. The result is that it takes n over 4 times of application of the computational element one time, I say of length 1, to handle the next to the bottom level, n over 8 times, because there are n over 8 elements in the next level up, but they require a computational element to be applied length 2 times, n over 16 applications at the next level up, and they require at most 3, each of them requires at most 3 applications of the computational element, and so on. We're now continuing to analyze heapify, and we have given an algorithm for doing it, and we've seen how much time t of n will be. The formula at the bottom for t of n expresses what we've just said. Over log n over 2 levels, we have first 1, I equals 1 length that has to be done for n over 2 to the 1. That is to say, n over 4 elements. And then for I equals 2, we have 2 elements of work to do for each of n over 2 over 2 to the squared. That is to say, n over 8 elements, and so on. So the overall T of n is given by n over 2 times the sum that's given. Now let's examine that sum. It's of the form I times a half to the I, and we have a formula for sum of I times some constant to the I. We can look at that sum evaluated for m equals infinity, and we see that it is a constant. That is to say, it's independent of n. And so while the sum, only up to log n over 2, is dependent on n, nevertheless, it's bounded above by this constant. And so we can say that this sum takes time theta of 1. When we multiply the sum, which is time theta of 1 times n over 2, we get theta of n. That is to say, heapify takes time order of n. Now we're in a position to analyze the whole heap sort. To do that, we need to analyze the situation once we've had a heap. In a heap, the maximum element is at the top. So of all the n elements, the maximum is at the top. It belongs in the nth position, and so we'll put it there by swapping it with the nth element, which is at the end, the rightmost leaf of the tree. That puts the nth element into place, but now into the top position we have no longer a maximum, and we have a file of size n-1, all but the last element, yet to get things put into place. So what we need to do is to take that element at the top of the tree and reheapify it reheapify the tree with regard to the n-1 elements remaining. When we do that, we will have a heap of size n-1 with its maximum at top. We can take the max and put it into the n-1th position. We do that by swapping with the n-1, the present n-1 element, and that requires yet another reheapifying, but now with regard to n-2 elements. The result the reheapifying involves starting at the top and going down the number of levels to get down to that level where the last unsorted element is. That is to say that since there are I-1 of them, that'll take log I-1 steps. And for each step we do this computational element where we compare a parent with its two children, possibly swap the parent with one of its children, take that the thing in the new position where the parent was swapped into, and compare it and do the computational step with its two children, and so on. So there's one of these computational steps per level. That is to say, T of I for reheapify for the ith step is simply proportional to the number of steps. That is to say, it's theta of log of I-1. That gets the next get ready for the next stage, and so the loop body involves doing putting the element, the ith element into ith element from the end, from the n. Let's see, we're talking about the first filling the nth, then the n-1, then the n-2 tooth. That's I, and that element is swapped with the max and then we have to reheapify. So the swap takes theta of 1. The reheapify takes theta of log I minus 1. Theta of log I minus 1 dominates theta of 1. So the time for the loop body is theta of log I minus 1. The result is that the loop, it's overall, takes sum I equals 1 to n minus 1, each time putting a new element into place of the loop body, theta of log I minus 1, and we have a summation formula for that guy, that sum, and that is theta of n log n. So what we know then is that the loop of heapify takes theta of n log n. So now we're in a position to finish the analysis of heap sort. Remind you that it begins by a heapify stage, and then it's followed by a loop. We've seen that the time for heapify is theta of n, and the time for the loop is theta of n log n. The result is the sum of those two. Now, of course, theta of n log n is slower. That is to say, it dominates theta of n. So the overall time for heap sort is theta of n log n, at worst. Comparing this to insertion sort and quicksort, we see that both of those have worst cases theta of n squared. And so heap sort, in worst case, is faster than both insertion sort and quicksort. Now let's move to merge sort. In merge sort, if we have a file of size 1, we are done. Otherwise, we divide it into two halves. Well, they may be off by one. If n is odd, you divide it into a half-size file of even size and one of odd size, approximately off by difference by 1. And then we merge those two sorted subfiles. I want to talk about analyze the merge step. Because the overall time of the algorithm, T of n, is going to be T of n over 2, plus for sorting the first half, plus T of n over 2 for sorting the second half, plus the time for merge. And we need to talk about the time for merge. So let's talk about a subfile of total size m that is divided into two parts, essentially size m over 2 each. And let's look at the merge of those m elements into an m element total file. The way we do that is we initialize two pointers, one at the end of the first subfile to be merged, and the other at the left end of the other subfile to be merged. That is to say, the pointers are pointing to the least elements of those two subfiles. What we're trying to do is to take out the least of the element in the total subfiles, and that will be the least of the two being pointed to. Say it's the one on the left subfile. So that's the lesser or equal of the two elements that are being pointed to. We take that guy and put it into the result subfile, and then we move its pointer down one. So notice that what had to happen was a comparison between two elements being pointed to, a comparison, moving one of them, writing it into the subfile, and a shift of the pointer.
That set of 3 steps we'll call our basic computational element. Okay, so we've so far done one of computational element. We then go on to we're in the situation of the second of the pair of subfiles picture. And now we compare, again, the 2 elements that are pointed to by their respective pointers, and we do the computational element. We compare, we take the smaller, put it in place, and move its pointer. So say that the smaller happens to be the first element of the right subfile. So after that happens, its pointer's been pushed along, and we have pointers in position 2 for both of the subfiles. Then, again, we compare what the 2 pointers are, we do this computational thing, and we push one of the pointers. Let's say the lesser of those 2 is the one in the right subfile, so its pointer gets pushed along. The point is that we're doing this computational element, and every time we push a pointer along, and we stop when all the pointers have moved past the end of their subfile. That means that since there are m elements total, and we move one pointer, one element each time, there are m applications of this basic step, which is a comparison plus a pointer shift plus a write. That is to say, merge takes theta of m comparisons. The result is going to be that merge sorts analysis is going to be T of n equals T of n over 2 plus T of n over 2. Those are the 2 merge sorts plus theta of n, the merge. Let's repeat that in the next slide.
The merge sort algorithm, of course, when applied to elements 1 through n, requires merge sorting the elements of the first half, merge sorting elements of the second half, that is to say n over 2 and n over 2 respectively, and then combining them with a merge. We've seen that a merge of m elements takes theta of m comparisons. Thus, if T of m is the time needed to sort m elements, then T of m is T for the first m over 2, the time to sort the first m over 2, plus the time to sort the second m over 2, that is to say T of m over 2, plus the time to combine them with a merge, and that takes theta of m time. That equation is a recurrence relation that can be rewritten as T of m equals 2T of m over 2 plus theta of m. This recurrence relation is what we're after and have to solve. That is to say, we need to find a solution of the form T of m, T of n equals theta of some function of n. And in the videos upcoming, we'll see that the solution of that is T of n equals theta of n log n. What we've concluded is that merge sort is a theta of n log n algorithm. So is heap sort. But the analysis was quite different. In merge sort, we analyzed by producing a recurrence relation which we had to solve, whereas in heap sort, which is an iterative algorithm, we had to generate a summation, and analyze that summation. Before we close this video and tell you to go on to the next video, which involves how to analyze this form of recursive algorithm to produce a recurrence relation and how to solve that, we pose these worksheet questions. The worksheet, you are to copy these questions down onto your computer, answer them, and submit that into Gradescope. And you need to do that before the very next class, in which we're going to begin to do exercises.